Hey, welcome to our second help video on 8-26, working with double displacement reactions. And when we left off, we were on number 6. Number 6 is the reaction of nitric acid, which is a really strong, one of our 6 strongest gases. And it's going to react with a salt solution of lithium cyanide. Cn minus is our cyanide ion, one of our polys that we learned. And when we mix these two solutions, being one of our 6 strong acids, nitric acid will dissociate 100%. The H pluses will break off, leaving the NO3 minuses floating around. And we're mixing it with Li pluses and Cn minuses. And it's quite conceivable when these ions are all floating around that these H ions will bump into the Cn ions. And when that happens, we make HCN. HCN can be called hydrogen cyanide. It can also be called hydrocyanic acid because Cn minus is one of our negative polys. When we have the hydrogen on it, we name it like an acid. And this is one of the rare ones where we actually put hydro in front because there are other acids that are called cyanic acid. So on this one, if you remember back to our acid-base chapter, we learned to name this as hydrocyanic acid. Now this is the one that is a gas at slightly higher than room temperature. Earlier on one of the problems back here, I mentioned that H2S, hydrogen sulfide, is a gas at slightly greater than room temperature. Well, that is true, but it is a gas at much lower temperatures than that. So this one, H2S, is something that is a gas. This hydrogen cyanide or hydrocyanic acid is a liquid at room temperature, but it is volatile and it goes to a gas easy at slightly above room temperature. So when the H's bump into the CNs, they can bubble out of solution, leaving in the solution Li pluses and NO3 minuses. If we look up here on our chart, lithium, you'll see, is not even on our chart. So, looking up lithium nitrate, it is soluble. Most nitrates are soluble, so they will stay floating around. So what's the driving force on this reaction? It is gas. Gas is produced. On our 7th reaction, they tell us again it's an acid-base neutralization reaction. That's a special category of double displacement, where water will be our product. Here we have sulfuric acid, one of our 6 strongest acids. This one will dissociate 100% in solution, so we'll have SO4 2 minuses floating around. We will have H pluses floating around. And when that is put together with an aqueous solution of strontium hydroxide, strontium's 2 pluses will be floating around. OH minuses will be floating around. What happens here? Well, the SR 2 pluses will bump into the SO4 2 minuses. In this particular case, again, we don't have strontium on this chart either. But when we look on other charts, we will see that SR SO4 strontium sulfate, it is insoluble. It will precipitate out of solution. So when the first thing here, the strontiums, bump into the sulfates, they will join up and water cannot keep them separated. They'll precipitate out of solution. In a double displacement reaction, the first thing from the first compound will join up with the second thing from the second compound. So the H's will join up with the OH's. HOH is water. So when we have a double displacement reaction, you'll also, that is an acid-base neutralization reaction, you'll often see the H written in front of the OH in respect to the fact that this is a double displacement reaction, but HOH can also be written as H2O. It is water, and that is a liquid. How do we balance this thing? Well, first we have to realize that strontium's 2 plus. We learned the sulfate ion is 2 minus. We crisscross and reduce those. It is SrSO4s. I have 2 hydroxide ions here. I have 2 hydrogen ions there. That means we will form 2 waters. or 2 HOHs, and that reaction will then be balanced. Our final one of these, we have LiOH, lithium hydroxide. It is aqueous, an aqueous solution. We also have an aqueous solution of sodium nitrate, and we're pouring these two together. The first thing here, when we mix these solutions together, we'll bump into the second thing here in a double displacement. The first thing from the first compound joins with the second thing from the second compound. However, when they bump into each other in solution, we have LiNO3. LiNO3, lithium nitrate. Lithium nitrate is soluble in water. It will stay aqueous. We also would have the NAs bumping into the NOHs. NaOH is also soluble. NaOH. There's the sodium. There's the hydroxide. It is soluble. So when we're looking at this one, you might have had trouble. The lithium nitrates, you may have not been able to tell. I can't even see if the lithium nitrates are on that chart. You might have had trouble knowing if it was soluble or insoluble, and I apologize for that. Hopefully you looked at another chart. But if you didn't, you now know that that would stay soluble. Since everything here remains in solution, there would be no precipitation, no precipitate formed. There will be no reaction happening. We also don't form a liquid. We also don't form a gas. So that would be a no reaction. On this next one, we are supposed to write the double displacement reaction of aqueous barium nitrate and aqueous magnesium sulfate. How do we write this? Well, when we go to write this, we have the BaNO3. Where did they get that? Barium's 2 plus, nitrate's 1 minus, crisscross. We have MgSO4. Magnesium's 2 plus, the sulfates are 2 minus, crisscross and reduce, MgSO4. Aqueous means that water will pull these apart. So we'll have barium ions floating around. For every one barium ion, there would be 2 nitrate ions. In the next container, water would pull those apart. It's aqueous, so we'd have an Mg2 plus floating around and an SO4 2 minus floating around. Where did I get the charges? Magnesium's in the second family. It's always 2 plus, the alkaline earths. We learned the sulfate ion was 2 minus way back when we learned our polys. Barium also is in family number 2, the alkaline earth metals. They are always 2 plus. Earlier this year, we learned the nitrate ions are 1 minus. So when we pour those two together, we'd have the Mg 2 pluses floating around, the nitrate ions would be floating around. But the bariums are going to bump into the sulfates. What happens when the bariums bump into the sulfates? There's the barium. Here's the sulfate. They are insoluble. Water cannot keep them apart. They'll join together and precipitate out of solution as a solid. So this picture here is illustrating what happens when we pour those together. The bariums are going to bump into the sulfates. PPT stands for precipitate out of solution. We continue on to our final page. And here we're going to go back and review a little bit about writing net ionic and ionic equations. And we're going to review a little bit about spectator ions. So here we go. In this first reaction, we have zinc nitrate. We have sodium carbonate. How did I get the formula for zinc nitrate? Zinc's charge is always 2 plus. If you didn't remember that, you can look up on the chart, see that the zinc is 2 plus. We learned the nitrate's 1 minus, crisscross. The 1 goes there, the 2 goes there. We learned the carbonate ion was 2 minus earlier this year when we learned the polys. Sodium is in family 1 and is always 1 plus, crisscross our charges. When we do this reaction, the zincs are going to bump into the carbonates when they're floating around. What happens when the zinc ions bump into the carbonate ions? Well, there's the zinc. We go over to the carbonate column. They're insoluble. It'll precipitate out of solution. The sodiums are going to bump into the nitrate ions. We go up to the chart. Where's the sodiums? Right here. The nitrates are right down here. There it is. They are S standing for soluble, so they'll remain in solution. The zinc carbonates will precipitate out of solution, satisfying one of the three driving forces. So this will be a double displacement reaction. That's the chemical equation for it. The next one, they want us to write the ionic equation. In an ionic equation, if the substance is aqueous, we pull apart the ions. So we pull apart the zinc, 2 pluses. We pull apart the 2 nitrate ions, so the 2 goes in front. We just pull those apart. Then we're going to pull these apart. The carbonate ions are CO3, 2 minus. And then we would have the 2 sodium ions floating around. Again, when it's ionic, if it says aqueous, we pull them apart. It says aqueous over here. So we're going to pull apart the 2 sodium ions are going to be floating around. And there will be 2 nitrate ions floating around. 2 right in front. However, the S says water cannot pull them apart. So they will precipitate out of solution. They join together, these 2 ions join together, and water can't pull them apart. So when it is a solid written after it, you keep them together. The next thing they want us to do is write the net ionic equation. If you remember, on the net ionic equation, we write only the things that underwent changes. You only show stuff that had a change. For double displacement reactions, the changes will refer to things that are not able to remain in solution. When we look at this equation, then there's 2 nitrate ions on this side. There's 2 nitrate ions in solution on that side. There's no change on those. We have 2 sodium ions on this side. We have 2 sodium ions on that side. Nothing changed. So on those, we would cross these out. That is going to not be involved. No change there, no change there. What did change? We had zinc ions on this side, on the reactant side. We had carbonate ions on the reactant side. On the product side, those ions are not floating around anymore. So they underwent a change. So our net ionic has the zinc ions, it has the carbonate ions, and on this side, they're no longer ions free to float around, they precipitate out. Spectator ions referred to the ones that had no change, the ones that were the same on both sides. We had 2 nitrate ions on this side. We had 2 nitrate ions on this side. So the 2 nitrate ions did nothing. They are spectators. We had 2 sodium ions on the left side, the reactant side. We had 2 sodium ions on the product side. They did nothing. They are our spectators. More of the same in this reaction. We have aqueous silver nitrate. We learned silver's 1 plus. We learned nitrate's 1 minus, crisscross. The formula for silver nitrate is AgNO3. We had aluminum chlorides. Aluminum are 3 plus. Chlorides are 1 minus, crisscross, AlCl3. What happens? The Ags bump into the Cls, and on the table we learned that they would precipitate out of solution. If we look up on the table, we would see that the AlNO3s would remain in solution. We'll finish up 14, 15, 16, and 17 on our third and final video. I'm sure you're looking forward to finding out about 14, 15, 16, and 17. They'll be on our next video.